comes in. Um, and then also just so everyone's aware, I am recording this and I'll have the video up tonight and I can send it to you guys. Um, and then the email list is right here. So I can get that to you. Okay, so you guys got some time to work on the problem. Does anyone want to like start us off with? If you have the answer, if you don't, that's fine. Just like anything you're looking at for this one.
I have like a VR on a benzene ring, so then you're reacting it with MD to turn into a grenade.
Hmm.
And then it reacts with CO2 and forms like that ion intermediate, and you react it with HCl plus to coordinate it.
Okay, yeah. And what's the like the final product gonna look like?
Basically, the benzene ring with a carboxylic acid.
Mm, okay, sure, yeah, yeah. So I'll draw that up so everyone can see what we're talking about. Um, okay. So we got the benzene ring, and then we're reacting it with magnesium to form that Grignard. That Grignard's a really strong nucleophile. So then it's going to be able to attack the carbon on the CO2 just to basically stick that CO2 on there. But when you stick it on, that bond needs to be formed. So you're not going to get a carboxylic acid right away. You're going to get a carboxylate, which is just like the anionic form of carboxylic acid. So then step three is the acidic workup. You get your carboxylic acid. Um, so what that looks like is that. So that's the uh, benzoic acid. And then just gonna check that I'm recording correctly. Okay. I think I am recording, but I'll just keep this here. Okay. Um, all right. So any questions with that one? Does that look familiar to some people? Yeah, it's just the addition of CO2. I think we'll see it over. So, we'll kind of skip around and I looked at a bunch of these questions. Also, I'll just say it again. This is like a practice exam that I had available when I took this class, so I don't think you guys have seen it before. I just wanted to give you guys some new problems and we'll cover maybe about like a third of the exam, the practice exam, maybe half. We'll get through it as much as we can. And we'll cover like the most important stuff right away. Um, just so we'll skip around a little bit. So for this one, we're looking at B. I'll let you guys read that, but this is just for aldol. Um, and I'll give you guys a minute or two just to kind of digest it, look at it, and come to your own conclusion before we reconvene together and talk about it. So I'll give you guys a minute and then we'll talk about it. Hello. Hi. We're just looking at this problem B, and then we'll talk about it in a second here. But yeah. So this is from a practice exam that I had for my class. So,
Oh, yeah, your class?
mhm.
Okay.
Yeah. So I think it's new, but we'll we'll go over it together. Okay, so we can probably talk about it now that you guys had some time to look at it. Um, so for this problem, we're looking at aldol reactions, and we're just gonna wanna see which pairs of reactants form a single product. If it's not forming a single product, it's probably forming like a whole mixture of products where it's not desirable. It's kind of just a mess. So you want to get like the one that you where you actually just get one product. Um, the other thing to keep in mind is that for this one, it's important to highlight that this is happening at 6 Celsius, 6 degrees Celsius. Why is that important?
It won't go through condensation.
Yeah, yeah, exactly. And what does that mean for aldol? What is a condensation?
Your OH group is with the proton, so you have water as your byproduct.
Yeah, exactly. And so just so we're all on the same page, when we're thinking about the aldol reaction, um, especially if it's not undergoing condensation, you're probably gonna get a product that looks something like that. You're gonna get like carbon groups on left and the right, and then you're gonna have a carbonyl and a double bond. So that's the reaction that we're looking at. Okay, so does anyone want to throw out an answer that they think is that they found might be correct?
Number two from the left, then number four for the one on the far right.
Okay, yeah, sounds good. So why do you say number two, this one?
So that one doesn't have any alpha protons because it's just like a aldehyde. And
Okay.
then wait, actually, would the bottom one react with itself, like like
Oh, mm-hmm.
the like acetone, would it react with itself?
So for the purposes of this class, no.
Okay. Well then, yeah, so
hmm
then the acetone will just react with, like, the top one is forced to be the electrophile, and then the bottom one can be the nucleophile.
hmm Yeah. Yeah, and so the bottom one's the nucleophile because it has the alpha protons. The top one doesn't have any alpha protons, so it has to be the electrophile. Does that make sense? Okay. Yeah. And then just to point it out, this is an aldehyde proton, not an alpha proton. It's attached to the carbonyl carbon. And then on the left side, there's no alpha protons there. It's just carbons. Okay. So because we just have one nucleophile, one electrophile, we're going to get a single product, is basically what we're saying. Um, and we just have to know what those key things are that determine whether it's a nucleophile or electrophile. Okay. And then you said the last one, this one.
Mhm.
Okay. And why is that?
Because it's symmetrical and it's reacting with itself, and there's only one site where there are alpha protons as well.
Yeah. So, yep, reacting with itself, just one site, which is right there. We're gonna get a single product. And if you look at the other two that don't form single products, it's usually because there's multiple sites to form nucleophilic sites or something like that. That's usually what happens. Or both products can be a nucleophile. You get a whole lot of mixtures there. So yeah, that's the correct answer for B. Okay. And then I mentioned this. Oh yeah. yeah, it's reacting with itself and it only has one site for, yeah, for alpha protons.
Is it- Why is it the second?
The second one, this one? So for this one, the second one, we only have one nucleophile and one electrophile. Do you know which one the nucleophile is? It's going to be the bottom one, actually. So the nucleophile is going to be the one with alpha protons, the one that's going to be able to be deprotonated, have that electron density. And so when we're looking at the bottom one, um, these are methyl groups. So those methyl groups have H's on them, and those are alpha protons. And so we can deprotonate those, get some electron density there. And then the top one is interesting because the top one doesn't have any alpha protons. So that's aldehyde proton, and then no alpha protons there as well. So, yeah,
What about the third option though?
third one. All right. So for the third one, okay, yeah, when I was doing this, I also got tripped up on this one as well. So what is calling your attention on the third one?
Bottom, that one. Oh wait, actually, never mind. Never
Hmm.
mind.
Yeah, 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 yeah. Yeah. So there's both products can
Yeah, both of them.
form. Hmm.
Um,
Yeah, 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 yeah. So that's a problem too. So we just want one electrophile and the other one to be the nucleophile. And then we'll just look out for that. Okay. Any other questions about this one? Okay. So, um, and then I mentioned this earlier, but we'll kind of just skip around this practice exam. I'll send this one out to you guys too, so you guys can cover the other ones that we missed. Um, okay. So next we're gonna go through this whole page, just because I really like the reaction problems. So we can look at this first one, and we can just talk about it right away. When we're looking at this first one, what what calls your attention? What do you see right away?
Happy ended as a functional
Hmm.
group. H2O, H2O support, that tells you that's an acidic condition, so that tells you the only way an H2 can do those kind of conditions is with hydrolysis. So
Hmm.
hydrolysis is gonna be happening and it's gonna form your silic acid.
Hmm. Yeah. Yeah, 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 exactly. So in this reaction, we're going to form a carboxylic acid. Um, and that is going to come through hydrolysis. So usually when you have H2O as a reactant, you're going to break it apart. That's called hydrolysis. And so the H2O is going to form our OH that goes there. Um, and it's going to be under acidic conditions with the sulfuric acid as a catalyst. Um, okay. I guess one of the important things to keep in mind for this one is the order of carboxylic acid derivatives, which is like super important to know for this exam, and we'll like go over it as well throughout this practice exam. But when you're thinking about this, you know that yeah, but it's still right. Like it is going to form a carboxylic acid, but I still wanted to mention that whenever you're doing these reactions with carboxylic acid derivatives, just because it can happen doesn't mean that it will. You have to think about the reactivity, the stability of like these derivatives, and we'll go over that more. But in this case, it does occur. Amide can go into carboxylic acid. But yeah, just to keep that in mind. All right, so I would draw it out, but it's just like the same thing with the OH instead of the nitrogen there. Um, is that is there any questions on that one? Okay, we'll all right, we'll go down to this one. Okay, so I'll let you guys think about this for like 30 seconds, and then we'll come back to it just so everyone has a chance to think about it. Okay, so we can reconvene now. So when we're looking at this one, what is like, I don't know, like a red flag of, well, not a red flag, but like, what do you see that's immediately tells you what kind of reaction this might be? Yeah. And why is that important? Hmm. Yeah. Yeah. So this reactant, the sodium cyanoborohydride, is one that you guys have only seen for one reaction, which makes it really simple to identify what kind of reaction that will be if you see it. So if you see sodium cyanoborohydride, then it narrows it down to that reaction. And so what is that reaction that we're looking at? Does anybody know?
Can't remember like the name of it,
Hmm.
but the way I think about it is you basically just put whatever your like amine is and just like attach it to where the like the carbon is. And
Yeah.
kind of just like flip it, not flip it, but like, yeah, you just put it in place of,
Hmm.
and then you take off an H.
Yeah. Yeah. Yeah, exactly. So you yeah, you just stick it on there. And it's very similar. I think it was the last exam to like the imine and enamine reactions you had. It's very similar to those. So don't get it mixed up. But for this one, it's just yeah, it has like a super long name. It's like formation of substituted amines using ketones through reductive amination. Basically, just like what that means is, yeah, what you said. You just put the N there, the nitrogen, and then you're gonna reduce it with the sodium cyanoborohydride. Um, you guys have seen sodium borohydride before too, and that's a reduction agent. So I'll draw like the oops start, and then you said we just like attach it on, right? Okay. So that's what it'll look like. And then also just keep in mind that, yeah, like you just attach it on and then you also reduce it down. So we're not going to have a double bond there. We're just going to have a single bond for that one. Hmm. Um, yeah. Are there any questions with this one? Okay. Yeah, that's good. All right. So then looking at this one, what kind of reaction is this one? Just maybe the name of the reaction. Okay. So we're look for our reactants, we have an aldehyde and then a ketone. And then also one of like a big hint is also our temperature too. So whenever we see temperature, whenever they indicate temperature, they're usually like drawing our attention to one reaction. Okay, so this is the aldol reaction where we basically are reacting ketones with each other or aldehydes with ketones. And we're gonna form the aldol product, which is what we talked about in the previous question for on the other page. And then with the 6 degrees Celsius, we said that when it's really cold, it's not gonna form the condensation product. So we're gonna keep that OH there. Yeah. Okay. Um, okay. So does anyone have an easy way of writing out the product without going like through the whole mechanism?
Yeah.
Yeah. Okay. How would you do it?
First,
Okay.
and then the H is gone, and so the R group. So how I do this, yeah, So you start with the electrolyte first, and then that's when like. It's not butyl, I forgot the name.
Uh-huh. Yeah.
That's when that like goes where the H used to go, but it goes down, like. And
Mm.
then draw the rest of your stuff.
Hmm.
Like you flip the second one, like, and then.
So you're really close. So we'll start with the electrophile. Because I also like to start with the electrophile as well. And we'll just draw that out. And also oops. And then also um the electrophile and then aldol reaction is the one that becomes the OH, or is the one that like leaves when there's a condensation product. So okay, so we got the electrophile there, and then we'll stick on the nucleophile. But the site of the sticking is wherever we did the deprotonation, wherever we formed that nucleophilic site. Hmm. Yeah, so sometimes this nucleophile will flip if we needed to, if the nucleophilic site is on the right, but in this case it's on the left. So we'll just kind of like put it on.
So then that method then goes down,
Hmm.
and then you draw it as it is.
Yeah. Yeah, exactly. So this is the methyl. That's this one. And then so that one went down, and then we get our carbonyl up here, and that's our tert-butyl there. So that's what that product will look like. Oh, and then also, so you draw it out, and then yeah, and then your electrophile becomes OH. Don't forget about that. But that's how I like to do it too whenever I draw the product, because these exams, you guys don't get like that much time to take the exams. So a lot of wherever you can save time is super helpful, so you can dedicate it to more difficult problems. But yeah, that's how I like to just think of the product, um, just like super quickly like that. Um, okay. So in this case, we do form a product. What would it look like if we couldn't do an aldol reaction?
Would be any alpha protons.
Hmm. Yeah.
So like if, I guess the only site on that second reactant, if there was like a methyl group there, then there wouldn't be able to. Yeah, then you would be able to, wait, I think that's right.
Yeah. So okay, yeah. So with Clayson,
It's Clay, okay,
yeah.
I was thinking of Clay.
Yeah, exactly. They're like super close.
Yeah,
So yeah,
if there was just no alpha protons.
yeah, exactly. So with aldol, if you have one alpha pro, so like imagine this is a methyl. If you have one alpha proton, it'll work. It'll be fine, but you just wouldn't be able to do the condensation. Um, if you have two methyls, there's no alpha protons, and yeah, there's no reaction there. Does that make sense? Okay, because you need to deprotonate the alpha proton in order to form the nucleophile.
There was no condensation. How would it look different?
So back to this one. So when we don't have a condensation, this is the product that we get, is the product with the OH. And we did that because of the temperature too.
Yeah. Okay.
Yeah. But imagine this temperature was not 6 and was like 30 or whatever. And they would tell you too, I assume. Then the condensation product would look like that. And so whenever you draw the double bond, if you're trying to do it quickly and you're not doing the mechanism, that double bond is drawn on the side of the electrophile as well. And it'll always be that way. So that's just like a quick way of drawing it out.
That would only be, um, there was one proton instead of two, if the temperature wasn't stated.
So if the temperature wasn't stated and there was
And
just
like you assumed it wasn't 6, like if they had talked about the temperature,
Mhm.
and let's say it's 30 degrees Celsius.
sure.
The starting material was with the added methyl group,
Uh-huh.
that's what you would get, or,
Yeah,
okay.
yeah, exactly.
Nice. Okay. But
Yeah.
if there wasn't that there, then you get the other one with the double bond. Okay,
Yeah. So, yeah. So even if the temperature is there, so that we can form the condensate, if there's just no methyl or no alpha protons in the product, oops, then
Yeah,
yeah, yeah. Like, so then you won't be able to form the condensation product because the condensation product also comes from deprotonation. So whenever you want to deprotonate, you gotta have that. Uh, will the temperature always be stated? I'm not like super sure, but I would assume so because it is important to know. If it's not stated, then assume that it's room temperature, which means that it will form the condensation product. Um, but I don't know. If I was them, I would state it. And just keep it simple. Um, but yeah, if it's not there, then do condensation.
So that's just or
Hmm. Yeah. So actually, I'll erase this again because we were talking about hypotheticals. Okay. That's the answer for for the question. So does that make sense? I can talk about it. So like this is the answer for this problem. If we had this methyl, that would be the answer. Yeah. Yeah, I didn't make that distinction too much, but yeah. But yeah, that's the answer that we're looking for. Okay. All right. I think we can go over to the next one. Okay. So for this one, it looks like a reaction that was straight out of OChem 1. I but but you guys did learn about it. So I'll give you guys a minute to think about it. Because I also forgot about it. But yeah.
yeah.
But yeah, I'll give you guys a minute and you guys can look over your notes and stuff, and we'll talk about what the answer is for this one. Okay, so we can probably talk about it now. Um, so what kind of reaction is this one? Does anybody know?
Alpha.
Hmm. Yeah, yeah. So it's the one where you just stick a halogen at the alpha position, replacing alpha proton. Yeah. Um, so yeah. Um, so I'll just draw that out. That's what we started off with. And then we just add our halogen to the alpha position, wherever that alpha proton was. So yeah, that's what that looks like. That's the product for that reaction. Um, and does anybody know how this actually happens? Because it doesn't really seem like a carbonyl should react with halogen. Mhm.
Where's the carbonyl oxygen gets protonated by the water. Um, and then the OH will come back and deprotonate an alpha proton, and then it'll like resonate, or not resonate, but the double bond will move down.
Mhm.
And then is that called a, I forgot what that product is called, where it's like a OH with a double bond next to it. Is it just an emo?
Um, uh, oh, Eno, yeah,
I
it's
think,
Eno.
yeah,
Yeah,
the
it's Eno.
phenol, and
Uh-huh.
then the ER will come in, and then
Hmm.
I think, does it get re? Wait, I might have to draw it out, but yeah, I know like the BR
Yeah,
will come in after that.
the the what? The
Right,
other.
or, okay, so then yeah, the double bond will then attack the like BR2.
Mhm.
And then, oh yeah, and
Hmm.
then the a lone pair from the oxygen comes back down,
Hmm.
and
Hmm.
then you
Yeah,
deprotonate.
yeah, yeah, exactly. So I'll draw it out a little bit. Um, I guess yeah. So then the first thing is that with this reaction, the way that we get the ketone to react is that the very first step is what's it called? Tautomerization. So if you guys remember, yeah, so like we form like the tautomer. So when we I'm just gonna write this as R, and this is our ketone. Remember that whenever we have, this is like from OChem 1, but remember that whenever we have a carbonyl, it's not like that in solution all the time. It's actually in equilibrium with the tautomer, which is the one that looks like that. So then, so this is like also just in the solution. And that's the double bond that we can use to attack the BR, and that's how we attach that on there. Um, yeah, and then you do like some proton transfers to get this. But yeah, that's the reaction that we're looking at. But yeah, that's the halogenation of ketones there. You kind of just take the halogen that you have and just replace a alpha proton with it. And then it's also important to mention that this only happens once. So even though we also have another alpha proton at that site, um, we can't do it again because of PKAs and stuff like that. But yeah, does that make sense? Okay. Yeah, this one's like a little bit more niche, but also I guess it's important to go over it just in case it comes up. Um, all right, so let me look. All right, so I think next we can do the synthesis problem, just so we have enough time to do it. Um,
Material always noted, fast our material.
um, kind of. It's like it kind of comes down to context. Um, because like if you ever see like for this one for C, like if you ever see an aldehyde and a ketone, throw like aldol into the table and think about it and see like whether the catalysts agree with that. But it could also be another reaction too. Um, but yeah, just by looking at the reactants, there should be like a couple different reactions that maybe you could maybe think about. But yeah, I don't know. It kind of comes down to context. Hmm. Okay, so we'll scroll down to the synthesis. Um, so this exam has its synthesis problem, but we're actually not going to go over it. I have a different synthesis problem that we'll do. I'll share this one with you guys so you guys can try it, but I'm going to be so honest. I was looking at this. I even looked at the key and I still didn't know how to do it. So so we won't go over this one because it's like so evil. But after the exam, if you want to ask how it's or Lyman Roberts about this one, please do because I don't know like what's going on there. But I came up with this one. Um, which also looks kind of difficult, but we'll go over it too. Um, it's a couple steps, multiple steps. So I'll give you guys a minute or two to think about this one. Think about like some of the starting steps, and we'll go over it together. Hmm. Okay, so we can probably start talking about it now. Um, and even if you guys don't have it all done, it's okay. We'll go through it as well and just talk about some ideas that we got about this. So, first of all, when you're doing these when at least when I do these syntheses, I like to just look at my reactants, look at the products, and see like what they want me to do. So let's start with the reactants. With the reactants, what kind of product? What this is a product of what kind of reaction, essentially? Yeah, there's a. Mhm. Yeah, I think. Yeah, exactly. Yeah, so I think with the aldol and the Claisen reactions, those can sometimes be difficult to spot, especially like the Claisen one too. But yeah, the big hint is what I like to look at are these two. When you have this beta dicarbonyl, that's like a big sign that maybe Claisen was involved. Also, whenever you have this ester group over here, yeah, probably Claisen. Um, the other thing is this the product of a mixed Claisen or just like a simple Claisen? Hmm. Yeah. And what makes you think that? What do you see with that?
Our group and they match.
Mm. Mm-hmm. Mm-hmm. Yeah. Yeah, exactly. So with yeah, so this is the product of a simple Claisen, which is just molecule reacting with itself to form the Claisen product. If we number the carbons, we have of the R group. On the left side, we have one, two, three. And on the right side, we have one, two, three. and it's the same. It's just the propyl group there. So yeah. So this is the product of a Claisen. So we're kind of thinking backwards here. And let's just draw that product out or that reactant out. So what would that reactant look like from this Claisen?
Like divide that, like those, divide between the carbonyl,
Mhm.
that right side is is your reactant.
Yeah, yeah, exactly. So with the Claisens, you one of them loses its so the Claisen for just so we're all on the same page is between two esters. And so one of those esters is going to lose its O alkyl group. It's oxygen and carbons. So this left side doesn't have an O alkyl. So the left side is lost it, and the right side keeps it. So the right side is the one is the reactant that forms this product. So I'll draw it out, and that'll probably make more sense. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So that's what that looks like. So if you got something like that, that's what the reactant for this glazing will look like. So immediately right before this final step is this. So now so that's one step down. We got a glazing. So then from this is an ester. Um, we can go a couple different directions with that. But now let's look back at the reactants and see how can I get from this alkyl halide to an ester? Does anyone have any ideas there? Yeah, it's yeah, alkylation. It's close. Why do you say that? Hmm.
And
Because what? There's more carbons in the ester?
it's like to ester, so.
Yeah. So this is a couple steps. And yeah, you're right. That's like the big hint. That's like super sneaky, is that this ester has 4 carbons and this alkyl bromide has 3. So we added 1 carbon somewhere along the way. So that narrows it down a little bit. Yeah.
Can you react, esters like this with like, I don't remember, it was like, I thought it was like a base in step one, and then like step two was like a alkyl halide like that, but I might be thinking of something else.
Base and then oh, and then the alkyl halide. Maybe you might be able to. I think there might be like different solutions to this one. Um,
I just need, I'm trying to find.
The green or whatever.
Oh, no, I'm not,
you're
I'm thinking
okay.
of like
So you
this, but that's not.
oh yeah. So a little different. So we threw out Grignard, um, because that's a good way to alkylate. Um, so let's think about that. So let's say we have our bromine, um, and we form our Grignard, which is with our um magnesium. Okay, we get our we get that. Okay. So what can we do with the Grignard? We did talk about this earlier today. But I think you weren't here yet. Sorry. Uh-huh.
react it with CO2 and H3O, you can the carboxylic acid.
Hmm. Yeah. Yeah. So that's kind of like the key here is that um when we whenever we're there's more carbons in the product, we're gonna add some carbons. And there's a couple different ways of doing that. We can either alkylate with the alkyl halides, or with like lithium or Grignards. You can also do cyano groups too that add the carbon, right, with the CN. You can also do CO2. And this one is like super niche, but I think it was on my exam. That's why I remember it. But yeah, the CO2 reaction is does come up, even though it seems minute. But yeah, so we talked about it earlier today, so I won't like spend like too much time on it. But so we have our three carbons, and then this is our fourth carbon, and then we kind of just add on our CO2. And remember, we have the acidic workup, so it's actually neutral too. Okay, so then from carboxylic acid, we're trying to get to our product. How do we do that?
So, okay, then, okay, we need a methyl, so you need like an O and E, right?
Mm,
But it can do acidic or basic, right?
um, I think so. I'm not really sure.
O and E, something, something.
Hmm.
That's all I got.
So what are you trying to make? The ester?
Yeah.
Okay, yeah. So we're trying to go from the carboxylic acid to the ester. Um, does anyone have a good way of doing that? Carboxylic acid to ester. Ester formation.
I forgot the reagent.
Don't worry. Um the reagents are like hard to remember a lot of the times. But this one is like I would say a more high yield reaction. You see it like all the time. So we're talking about the Fischer esterification reaction. Did Howitz go over that? Fischer esterification? Okay. Okay. Um, it's so Fischer esterification is like the acyl substitution, but with like an
So, okay, oh
alcohol.
no, like,
So uh,
okay, wait, so you react the carboxylic acid with like a alcohol, ROH,
uh-huh,
is that what it is?
uh-huh, yeah,
Okay, yeah,
yeah. So I
ROH can be like, so for example, this with methyl is the R. Yeah. So,
mhm,
yeah.
yeah. So for our ester, this is the one we're trying to form. Our ester has O and then one carbon, which is a methyl. So when we're trying to add this on to form the ester, we're gonna pick an alcohol that has that matches that carbon. So in this case, we have a methyl. But if we had a ethyl, then we would do ethanol instead of methanol there. But yeah, this is the sterification reaction. I think Lyman Roberts went over it like a lot, but if I remember how it said that like he wouldn't focus on it too much. So, but yeah, with that, I'll just give you guys the reactants, and it's just the methanol under acidic conditions and heat to form the ester. I think in exams, like if you forget heat, it's not like a super big deal a lot of the time. So if you don't remember some of the reactants, it's okay. As long as you have most of it. Okay, so now we have our ester, and then the last thing we can do that's one step away from our product is just the Claisen. And with the Claisen, um, I'll just I'll also just write it out so that we have time. With the Claisen, you pick a base that matches your at like your carbons on your ester. So like these. So we had the methyl. We picked methanol. Now we're doing the Claisen. We're gonna pick NaOMe with the methyl on that, and then acidic workup. This is just part of the Claisen. Um, and then we get our product. I'll redraw it. Okay, there we go. Okay, so that was um yeah, it was kind of a lot. But but all the hints were there. All of the 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 clues were there for you. I don't think that you will get a synthesis problem as hard on the exam. I hope you don't. Because I didn't intentionally make this harder because I knew that we would talk about it. Um, so if you were kind of lost on this one, don't worry. I like picked a hard one for you guys. But we talked about it and yeah, so this is maybe just some things to keep in mind for synthesis. Just Grignard, CO2, place and stuff. Yeah.
Like, could you go back to the exams? Like this exam synthesis question?
Oh, the other one? Yeah. Yeah, I can show it too. I'll send this PDF and the key out to you guys, just so you guys have some extra problems to work on tonight. Um, yeah, but yeah, for this one, like I tried, but like I don't know. Maybe I was missing something. It was just a little weird to me. But